section, let's discuss about the solution steps adopted in Thevenin's theorem in order to solve a given network. For that, let's consider a general circuit like this. In this circuit, we need to find out current flowing through the load resistance RL. So the first step in Thevenin's theorem is we need to remove the branch impedance of interest. Here the branch impedance of interest through which we need to find out the current is RL. So we need to remove RL from the circuit. So when we are removing RL, it becomes open circuited. Now let's mark the open circuited terminals as A and B like this. So we need to remove the branch impedance of interest and mark the open circuit terminals as A and B. And second step is obtain Thevenin's equivalent voltage. That is the voltage across the open circuit terminals VAB. In order to find out Thevenin's equivalent voltage, we need to move from B to A either in this direction or in this direction, and we need to add all the voltage drops. So in this case, it is very simple. VAB is nothing but the voltage drop across R3. In order to find out voltage drop across R3, we need to find this current. In order to find this current, we need to find equivalent resistance. So what is equivalent resistance? So these two resistances are a part of the circuit. So R1 plus R3 is R equivalent. And current is V divided by R equivalent, that is V divided by R1 plus R3. Now we can find out VAB, that is Thevenin's equivalent voltage. VTH is the voltage drop across R3. So I into R3 is nothing but V by R1 plus R3 into R3. Let it be equation number 1. So next step in this method is we need to obtain Thevenin's equivalent resistance or Thevenin's equivalent impedance. So it is to be noted that Thevenin's equivalent impedance is exactly equal to Norton's equivalent impedance or Norton's equivalent resistance. In order to obtain Norton equivalent impedance or Thevenin's equivalent impedance, we need to see the impedance through the open circuited terminals, keeping all independent sources to 0. Here only one independent source is available, that is voltage source. We need to make voltage source to 0 by short circuiting. So we short circuited this voltage source. So corresponding equivalent circuit is this one. Here when we are seeing through the open circuited terminals, the impedance seen is like this. R2 is in series with the parallel combination R1 R3. So R2 plus R1 R3 divided by R1 plus R3. Further simplifying, R2 into R1 plus R3 plus R1 R3 divided by R1 plus R3 gives Thevenin's equivalent resistance. And fourth step is we need to draw Thevenin's equivalent circuit. We know Thevenin's theorem states that any linear active bilateral network with output terminals A and B can be replaced by a voltage source, that is VTH, in series with an impedance or resistance. That impedance or resistance is termed as Thevenin's equivalent resistance or Thevenin's equivalent impedance. And this voltage source is termed as Thevenin equivalent voltage, and this circuit is termed as Thevenin's equivalent circuit. So next step is to draw Thevenin's equivalent circuit. This is the Thevenin's equivalent circuit. VTH is obtained as VR3 divided by R1 plus R3, and RTH is obtained as R2 plus R1 R3 divided by R1 plus R3. And the last step is we need to reconnect the load resistance which we removed in first step across the open circuited terminals, and we need to find load current IL. So this is the equivalent circuit. This is the Thevenin's equivalent circuit. Across that we need to connect load resistance which we removed earlier, and we need to find out IL. How to find out IL? IL is equal to voltage divided by total resistance. The voltage is VTH and total resistance is RTH plus RL. So IL is equal to VTH by RTH plus RL. In this way, we can find out the solution of a given network using Thevenin's theorem.